Polynomial Theory Part 3. The theorems we're going to cover in this demonstration include the exact number of zeros theorem, the rational zero theorem, the complex conjugate pairing theorem, and the algebraic conjugate pairing theorem. The exact number of zeros theorem is stated below. If a polynomial is of degree n greater than or equal to 1, then the degree of the polynomial is equal to the number of solutions in the complex number system, counting multiplicities. So here's an example. Given the following polynomials, determine the number of solutions the polynomial has in the complex number system. If our first polynomial is 4x cubed minus 2x squared minus 7x plus 1, we simply look for the degree of the polynomial to determine the exact number of solutions that it has. And in this case, the degree is 3. So the answer is 3. Which means that there are 3 solutions in the complex number system for this polynomial. Exactly 3. Our second example is the polynomial given here. Negative 5x to the 4th plus 2x cubed plus 17x squared minus 4x plus 7. And again, we apply the same kind of thinking. So we simply say, what's the degree of this polynomial? And in this case, the degree is 4. And this means that there will be exactly 4 solutions to this polynomial in the complex number system. The rational zero theorem is stated here. If a polynomial has integer coefficients, then every rational zero of the polynomial is of the form p divided by q, where p is a factor of the constant term and q is a factor of the leading coefficient. So let's look at an example. Determine the possible rational solutions for this polynomial. 4x cubed minus 2x squared minus 7x plus 1. First, we list out all the factors of 4 and the factors of 1. We have the factors of 4 at 1, 2, and 4, plus or minus. We also have the factors of 1 as 1 or negative 1. Now we form all possible ratios with these numbers. Factors of 4 are the denominator, and factors of 1 are the numerators. So we have this list of values: 1 over 1, negative 1 over 1, 1 over 2, negative 1 over 2, 1 over 4, and negative 1 over 4. And we may shorten this list up a little bit by saying 1, 1/2, and 1/4, with a plus or minus on the outside of the curly braces. And this is merely a shorthand to describe all the possible solutions for this application. So let's look at another example. Determine the possible rational solutions for this polynomial. Negative 5x to the 4th plus 2x cubed plus 17x squared minus 4x plus 7. First, we list out all the factors of 5 and the factors of 7. We have factors of 5 as 1 and 5 with a plus or minus on them. We have factors of 7 as 1 and 7 with a plus or minus on those as well. Now we form all possible ratios with these numbers. Factors of 5 are the denominator and factors of 7 are the numerator. So we have the following list: 1 over 1, negative 1 over 1, 1 over 5, negative 1 over 5, 7 over 1, negative 7 over 1, 7 over 5, negative 7 over 5. And when we apply our shorthand notation, we have 1, 7, 1/5, 7/5 inside of curly braces with a plus or minus on the outside. Some cautions about the rational zero theorem. The rational zero theorem does not say any of these members of the list have to be solutions. The theorem says if a polynomial has solutions that are rational numbers, then they must be members of this list. So let's look at an example that demonstrates the cautions that were described earlier. Suppose we have a polynomial x squared minus 7x minus 10. If we generate a list of rational solutions according to the theorem, we have plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10 as possible rational solutions to this polynomial. But if you check these results, none of these solutions work. This states the solutions must be either irrational numbers or complex numbers, or some combination of those. The complex conjugate pairing theorem is stated here. If a real coefficient polynomial of degree n greater than or equal to 1 has a root, and we'll call that root r1, and it happens to be equal to a plus bi, some complex number, then a second root to the polynomial must be a minus bi, which we label as r2. And if you notice, a plus bi and a minus bi are complex conjugates of each other, hence the name. So let's look at an example. The polynomial x squared plus 1 has I as a root. By the complex conjugate pairing theorem, negative I must also be a root. The polynomial x to the fourth minus 1 has negative I as a root. By the complex conjugate pairing theorem, positive I must also be a root. If we solve x cubed minus 1 equal to 0, we get 1 as the real solution. The other two solutions may be found by the quadratic formula. And using the difference of cubes factorization, we have x cubed minus 1 equal to quantity x minus 1 times the quantity x squared plus x plus 1. Using the quadratic formula on x squared plus x plus 1 yields this result. Negative 1 plus or minus I times root 3, and all of that divided by 2. If we write these slightly differently, we have negative 1/2 plus root 3 over 2 times I. We also have negative 1/2 minus root 3 over 2 times I. Notice these are complex conjugates of each other. So here's another example of the complex conjugate pairing theorem in action. We were able to determine one complex solution with a plus I root 3 over 2, and we're immediately able to determine that minus I root 3 over 2 has to be the imaginary part of the other solution, or the complex conjugate. Cautions about the complex conjugate pairing theorem. First thing is that it only works if the coefficients are all real numbers. Complex coefficient polynomials do not need complex solutions to come in pairs. You must already have determined one of the solutions to be complex. After one solution is determined to be complex, then another solution will be its conjugate. So we have to pay very close attention to the conditions of the theorem. The theorem specifically states if you have a real coefficient polynomial whose degree is greater than or equal to 1, and you know one of the solutions happens to be a complex number, then you are guaranteed by the theorem that another solution must be the complex conjugate of that other root. Here is an example demonstrating this caution. Consider the complex coefficient polynomial x squared plus 2 minus I times x minus 2i. So here we don't have real coefficients, we have complex coefficients. The solutions to this polynomial are I and negative 2. Notice that the conjugate of I, negative I, is not a solution to this polynomial. And that's because we do not have a real coefficient polynomial. We have a complex coefficient polynomial. The algebraic conjugate pairing theorem is stated here. If a polynomial has rational coefficients and a solution is of the form a plus b times the square root of c, then another solution, called R2, must be of the form a minus b times the square root of c. Now this theorem is very similar to the complex conjugate pairing theorem, but it's a little more specific in that it uses only rational coefficients instead of all real numbers. And we also see that we are dealing with a plus b times square root c and a minus b times square root c. So we have these algebraic conjugates forming pairs of solutions. Let's see an example. The polynomial x squared plus 5x plus 7 has rational coefficients, and one solution is -5 plus root 17 over 2. Another solution must be its conjugate, -5 minus root 17 over 2. And I invite you to check these solutions to see if they truly are solutions by using quadratic formula. Here's another example. The polynomial x cubed minus 5x squared minus 7x has 5 minus root 53, all that divided by 2, as a solution. Another solution to the polynomial must be 5 plus root 53 over 2. And again, I invite you to check both of these solutions to see if they truly are solutions to the polynomial. The other solution, of course, is 0. Some cautions about the algebraic conjugate pairing theorem. All the coefficients to the polynomial must be rational numbers. So they have to be counting numbers, whole numbers, or integers, or integer divided by another integer to qualify for use of the theorem. One solution must be in the form a plus or minus b root c. The square root is necessary. If a solution has a cube root or a fourth root, it is not true that its conjugate will also be a solution. So the square root is a necessary component as part of the known root that comes from the solution process for the polynomial. Consider x cubed minus 2 equals 0. The solution set to this polynomial is cube root of 2, the cube root of 2 times -1 plus I root 3 over 2, and cube root of 2 times -1 minus I root 3 over 2. Notice that the coefficients are rational numbers, but the solution cube root of 2 does not have a conjugate paired with it. You may also notice that the complex solutions are conjugates of each other. Thank you for your time and attention.